Let's continue talking about electrophiles in nucleophiles. Again, to remember, nucleophiles are electron-rich species, and electrophiles are electron deficient. Without say that we are being asked on a problem to identify what is the place in the molecule that could be likely attacked by a nucleophile. So if you're being asked what place, say, or what atom is, say, more likely to have a nucleophilic attack, so to be attacked by a nucleophile. What places? So what this question is asking is to identify the electron deficient places. So those would be, remember, think about electrostatic for a second. So if something in like opposite charges will attract. So, and you can keep that in mind. And so if something is electron deficient, so some sort of positive charge or delta positive, then it would be attacked, susceptible of being attacked by an electron-rich species. So say negative attracted to positive, let's say. So if you have a molecule like that and you're being asked what place is more likely to be attacked by a nucleophile, and say that I had just do a generic nucleophile. And I'm going to draw a few molecules here. Now I have, this is a metal. And I have here another molecule. So that is ethyl fluoride, that's acetyl chloride, that is boron, it's not trifluoride, but here we have, I'm going to change it and just going to put metals. And that's an oxime of acetone. All right, point is, what place or what atom is more likely to be attacked by a nucleophile? So keep in mind, this is electron rich. So we're going to find places here that actually are electron deficient, and those will be the ones that are likely to be attacked. So here you have a dipole pointing towards the fluorine. Here, this carbon is not directly attached to any electronegative atom, any electron withdrawing group. So it's likely the nucleophile is going to attack here. And you need to draw two arrows because, and let me just point to the fluorine, because you cannot break the octet. Remember, we have here two arrows. Now, next molecule. I know we have a dipole here, but also you have noticed, here you have the contribution of resonance and also the difference in electronegativity. And on top of that, you have another dipole here. So that carbon is very much electrophilic. So would be attacked by a nucleophile. So I'm just going to draw my, say a little higher. Just want to make an arrow. And so my nucleophile king will attack right here. And I need to draw a second arrow because I cannot expand the octet. Now in this species here, this carbon is not electrophilic, nothing there that is directly attached, that meaning electron withdrawing, such as this case. So not electrophilic, not electrophilic. But we know boron, here octet is incomplete. That means electron deficient. Therefore, it is susceptible to be attacked by a nucleophile, say that we have that. So that's the place that you would attack. Because boron has incomplete octet, you will not be breaking the octet rule by making a new bond. Now, in last molecule, we have here another example of a electrophilic carbon. It's right here. Here we have a dipole pointing in that direction. So that's delta positive. So that carbon is again likely to be attacked. I'm using the same nucleophile here. And because here, the carbon that I have shown here with a little yellow dot has 1, 2, 3, 4 bonds. So I cannot break the octet rule. I must move electrons towards the nitrogen. Okay, so the answer to my question was, what place is likely to be attacked? Where those places in the molecule that are electron deficient are the ones that would be more likely to be attacked by a nucleophile, which is electron rich. So negative or partial negative electron rich going to attack an electron poor place in the molecule.